Welcome to another episode of learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. Today, we discuss the solution of a problem from the section Real Analysis, and this problem is related to the concepts of Pointwise convergence and uniform convergence of sequence of functions. This question is placed in part C, which is a multiple select question. There can be more than one answer. The question carries 4.75 marks and the question ID is 704144. This question is suitable for all these examinations. Right. The given question is, for each positive integer n, define fn, a function from the closed interval 0 to 1 to the set of real numbers by fnx is equal to nx into 1 minus x whole power n. The power is for 1 minus x. For each positive integer n, fn is a function from the unit closed interval to R defined by fn of x is equal to nx into 1 minus x whole power n. The power is for 1 minus x. Which of the following statements are true? We are given four options. Option 1. The sequence fn does not converge pointwise on the unit closed interval. Option 2. The sequence fn converges pointwise to a continuous function on the closed interval 0 to 1. Option 3. The sequence fn converges pointwise to a discontinuous function on the closed interval 0, 1. Option 4. The sequence fn does not converge uniformly on the closed interval 0 to 1. Let's now discuss this solution in detail. We have a sequence of functions. For each natural number n, fn is a function from the closed interval 0, 1 to R defined by fn of x is nx into 1 minus x whole to the power of n for all n belongs to natural numbers. We first discuss the pointwise convergence of the sequence of functions. Right. At first we take x is equal to 0. Then fn of 0, put x is equal to 0 in the definition of fn of x, nx, therefore x is that 0. And limit n tends to infinity of fn 0 is 0, because each for all n fn 0 is 0. It is a sequence consisting of zeros alone, is a zero sequence. Therefore limit n tends to infinity of fn 0 is 0. It converges to 0. Let x is equal to 1, then fn of 1. So in the definition 1 minus x, 1 minus 1 is 0 is there, it is 0. And it is a 0 sequence, and it is a convergent sequence, converges to 0. The limit n tends to infinity of fn1 is 0. Option 3, let x belongs to the open interval 0 to 1. We mean to say that 0 less than x less than 1, then limit n tends to fn of x is equal to limit n tends to infinity of nx into 1 minus x to the power of n. And see what happens. Limit n tends to infinity of n is infinity, and x is 0 less than x less than 1. Therefore, 1 minus x also 0 less than 1 minus x less than 1. That means 1 minus x also belongs to the open interval 0 to 1. As n tends to infinity, it tends to 0. It tends to 0 because 0 less than 1 minus x less than 1, and its power n as n tends to infinity is 0. Therefore, limit n tends to infinity x times limit n tends to infinity of n into 1 minus x to the power of n. Limit n tends to infinity of n is infinity. Limit n tends to infinity of 1 minus x to the power of n is 0. So it takes infinity to 0 form, which is an indeterminate form. To evaluate this one, we convert it first to infinity by infinity form. So how do you do that? So this will be x times limit n tends to infinity of n by 1 minus x to the power of minus n. Then it converts into infinity by infinity form. Now we use L'Hopital's rule, the so-called L'Hopital's rule. That is x times limit n tends to infinity of the derivative of n with respect to n 1 by the derivative of 1 minus x to the power of minus n with respect to n is 1 minus x to the power of minus n into ln of 1 minus x. This is you are using the definition of the derivative of a power x. The derivative of a power x is a power x into ln a. So the same thing what we have written. This is by L'Hopital's rule. Now x by 1 minus x, limit n tends to infinity of 1 minus x to the power of n. Bring it to the numerator, this one. 1 minus x lies between 0 and 1. As n tends to infinity, it will tend to 0. This will tend to 0 because 1 minus x belongs to the open interval 0 to 1, as x belongs to the open interval 0 to 1. Right. So, as n tends to infinity, in all cases, it tends to 0. Thus, limit n tends to infinity of fn of x is 0. We say, let us say this is a function f of x. For all x belongs to 0 to 1, that means the sequence fnx, the sequence fn converges pointwise to f on the closed interval 0 to 1. Right. Let's call on the options. Options are here. And the first option says it does not converge pointwise, whereas it converges. Therefore, option 1 is not true. Option 2 says it converges pointwise, yes, pointwise to a continuous function. So it converges to fx. What is fx? Fx is equal to 0 for all x belongs to the closed interval 0 to 1. That means fx is a constant function and it is a continuous function. Every constant function is continuous function. Therefore, it converges pointwise to f, and where f is a continuous function. Thus, option 2 is true. Right. Option 2 is true and option 3 is not true. Why? Because the function f is a continuous function, whereas it is given here is discontinuous. Therefore, option 1 is not true because it is converging pointwise. Option 3 is not true because the limit function f is a continuous function, whereas it is given here it is a discontinuous function. We continue the discussion in the next slide. So now we are left with only one option, that is the sequence fn does not converge uniformly on 0 to 1. That means we have to discuss uniform convergence of the sequence. So, and before that, we have already seen that the sequence Fn converges pointwise to f, where f of x is equal to 0 for all x belongs to 0 to 1. So, to discuss the uniform convergence, let us recall a famous test called MN test. What does it say? It says let D be a subset of R, let sequence Fn be a sequence of functions converging pointwise to f on D. Let Mn is the supremum of mod of Fnx minus Fx, where the supremum is to be taken over all x belongs to D. Then the theorem the test says the sequence Fn converges uniformly to f on D if and only if limit n tends to infinity of Mn is 0. Right? It is the Mn test for the uniform convergence of sequence of functions. Sequence, not the series. Right. Let Mn is equal to supremum of x belongs to closed interval 0 to 1 mod of Fnx minus Fx. Let phi of x be mod of Fnx minus Fx, and that is mod of nx into 1 minus x to the power of n minus Fx is 0. That is phi of x is nx into 1 minus x to the power of n. And to find out the supremum, we find the maximum of phi of x. And we want to find the maximum of phi of x, for which we differentiate and equate to 0 and find out the critical points. So phi prime of x, differentiate with respect to x, and simplify, we will get n into 1 minus x to the power of n minus 1 multiplied by 1 minus x into in brackets n plus 1. And phi prime x is equal to 0 will give you two values, x is equal to 1 and x is equal to 1 by n plus 1. These are the critical points. These are the critical points. Right. Now, phi double prime x. So, we take the second derivative test. Phi double prime x, differentiate once again after differentiation. This is all what you get it. Now, f double prime at 1 by n plus 1. So, 1 minus x into n plus 1. This factor will become 0. This whole factor will become 0. You are left with minus n into n plus 1 into 1 minus 1 by n plus 1 to the power of n minus 1. This becomes 0. You are left with minus n into n plus 1 into 1 minus 1 by n plus 1 whole to the power of n minus 1. And this is, you can see very easily, this is negative because of minus sign here. It is negative. When it is a double prime is negative at 1 by n plus 1, where 1 by n plus 1 is critical point, will tell you that phi x attains its maximum at 1 by n plus 1. Thus we find phi maximum. The maximum value of phi is attained at 1 by n plus 1. Substitute in this, substitute in n into x, 1 by n plus 1 into 1 minus 1 by n plus 1. Substitute in phi of x for x is equal to 1 by n plus 1. N into for x 1 by n plus 1, 1 minus 1 by n plus 1 to the power of n. We continue the discussion in the next slide. Right, we got phi max. Mn is supremum of mod of Fnx minus Fx, that is the supremum of phi of x, x belongs to 0 to 1, that is phi max. What is phi max? We have already taken here n into 1 by n plus 1 into 1 minus 1 by n plus 1 to the power of n. Simplify n by n plus 1, take the LCM and simplify, you will get n by n plus 1 to the power of n. This is 1 by 1 plus 1 by n into 1 by 1 plus 1 by n whole to the power of n. Now take limit n tends to infinity of mn. Limit n tends to infinity of mn. Limit n tends to infinity of 1 by 1 plus n. This is 1. Limit n tends to infinity of 1 by 1 plus 1 by n whole to the power of n is e. 1 by e. 1 by e. This is 1. This is e. So this is equal to 1 by e, which is not equal to 0. So now by mn test, it is not uniformly convergent. So by mn test, the sequence fn is not uniformly convergent to f on the unit interval 0 to 1. So what is given on option 4? The sequence fn does not converge uniformly to f on the closed interval 0 to 1. Yes. Yes, what is given in option 4 is true. It is not uniformly convergent. Therefore, option 4 is true. Now, summarizing all the options, the answer to this question is options 2 and 4. That is the detailed discussion of the solution of the problem from real analysis, which is related to the concepts of pointwise convergence and uniform convergence of sequence of functions. And in almost all examinations, you get questions on pointwise convergence and uniform convergence. For that, what you have to read is, what is pointwise convergence? How do we find pointwise convergence? Number 1. What is uniform convergence? And what are the tests for uniform convergence? All those things you have to make a good notes and work out all the questions that have appeared in the previous years and make a good notes ready-made for the next examinations. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure that we are going to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.